Hey guys, welcome to this video on discrete and continuous graphs. Hope you enjoy. Alright, before we go and make some exact graphs of real-world relationships, let's start with a more general discussion of what these graphs might look like. So let's start by trying to graph the relationship of every time you ride the subway, you must pay a $2.50 fare. So first things first, we're going to want to find our independent quantity and our dependent quantity. I think our dependent quantity is going to be how much you spend on the subway. And let's give that a variable name, y in this case. Our independent quantity is going to be how many subway rides you take. And let's give that a variable name, x. And before we go ahead and graph anything, let's create a quick table of values to find some combinations of how many rides you take and how much you have to spend on them. I think we can agree that if you take 0 subway rides, it doesn't cost you anything. For 1 subway ride, it costs you $2.50. For 2 subway rides, it costs you $5, etc., etc. So now it's time to take these combinations, these ordered pairs, and plot them on a graph. Alright, so here's our graph. Before we go ahead and draw these ordered pairs, let's quickly give it a title. Let's label the axes. And let's create a scale. On our horizontal axis, let's start at 0 and make every 2 notches 1 subway ride. On our vertical axis, let's start at 0 and make every 2 notches $2.50. Alright, now that we've got our scale all set, let's go ahead and plot these points on our graph. Alright, and our points lie on a pretty nice line, which isn't surprising because, of course, the subway ride costs the same amount every time, so on our graph, the points should go up by the same amount every time. Now, it might be tempting to draw a line through all these points. The question is, would that make sense? Well, note that if we drew a line, that would imply that you could take fractional or decimal subway rides, which doesn't really make sense. Subway rides, you can't really take half a subway ride or 0.76 of a subway ride. And if we connected all those dots, that's what the graph would be implying. So in this case, the best representation of this relationship is with a graph that is made up of individual points that aren't connected. This type of graph is called a discrete graph. So a discrete graph is a graph comprised of distinct individual points not connected. And a note, discrete graphs will come up whenever either of our quantities that are in question are things that must be counted by ones. That is, when either one of our quantities are things that just can't continue to be broken down into smaller and smaller parts forever and ever. Some common examples of things that can't be broken down forever and must be counted by ones are people. Anytime people are involved, you can't break people into parts. And anytime money is involved. While you can break down money into smaller and smaller pieces, into pennies for instance, you can't break down money forever. Alright, let's try another example. In this case, let's graph the relationship where you run at a constant speed of 6 meters per second. First things first, let's find the independent quantity and the dependent quantity. I think the dependent quantity is going to be the distance you run in meters, and let's call that y. And the independent quantity is going to be how long you run in seconds, and let's call that x. And before we graph anything, in the lower left-hand corner, let's create a table of values of some combinations of how long you run and how far you've run. Alright, now that we've got these ordered pairs, before we graph, let's give this graph a title. Let's label the axes. Let's create a scale. For the horizontal axis, let's start at 0 and have every 2 boxes be 1 second. And for the vertical axis, let's start it at 0 and have every 3 boxes be 6 meters. Now that we've got our scale all set up, Now it's time to go ahead and plot those ordered pairs. All right, once again, all our points happen to be on a nice line, which makes sense because you're running at a constant speed, so every second that goes by, you're going another 6 meters, so they should be in a line. But the question now is it appropriate or is it not appropriate to connect these dots? Well, drawing a line through these dots implies that every infinitesimally small moment of time you are traveling a little farther. That in a half a second or 0.32 seconds or 7/3 of a second, you've traveled another distance. And is that appropriate here? I think absolutely. When you're running, you are continuously running. It's not like you just magically appear 6 meters farther ahead the next second. You are constantly running maybe an inch at a time, or a centimeter at a time, or a millimeter at a time for every small enough piece of time. So in this case, it does make sense to connect our dots and draw a continuous graph. And a continuous graph is a connected curve or line. The big distinction here is that it's just connected. It doesn't mean continuing on forever and ever. Continuous just means connected, whereas before discrete just meant not connected. Continuous graphs will occur when both of our quantities are things that can continue to be broken down forever and ever and ever. Some common examples of such things are time. Time can always be broken down into smaller and smaller units. Distance. This can be height, length, depth, distance traveled, anything at all involving distance, you can always break down into smaller and smaller pieces. And temperature. You can always break temperature down into smaller and smaller pieces. All right, let's do some practice. In each of these, you'll be given a hypothetical situation, and our main goal is to determine whether the relationship would best be described by a discrete graph, which is not connected, or by a continuous graph, which is connected. If you'd like, please try to label each of the axes and draw a quick sketch of what you think an appropriate graph would look like. For each, please pause the video, give it a try, then play the video to see how you did. Here's our first example. As you get older, you get taller and taller until your height eventually levels out. In this case, a continuous graph would be best to describe the relationship. Both your age, which is time, and how tall you are, which is distance, can be broken down forever and ever. And here's a little sketch of what that graph might look like. Second example. As it gets later at night, it gets colder, then it gets warmer again in the morning. Again, this relationship would best be described by a continuous graph, a connected graph. Both time and temperature can be broken down forever and ever, so a continuous graph is most appropriate here. And here's a little sketch of what that graph might look like. Third example. Each year, the number of students enrolled in the Mandarin Chinese class grew by 4. In this case, a discrete or not connected graph would best capture this situation. Since students are people and you can't break down people forever and ever, a non-connected graph made up of individual points, a discrete graph, would best capture the relationship. And here's a sketch of what that graph might look like. Fourth example. At the end of every month, you have $200 from your paycheck deposited directly into your retirement savings account. Again, this relationship would best be captured with a discrete graph. It's not like you're continuously saving every moment of every day. Instead, at the end of the month, in one lump sum, you are increasing your savings account, and so it's best not to connect these dots and to leave them as distinct individual points in a discrete graph. And here's a sketch of what that graph might look like. Here are some slightly tougher ones. Right before a serious safety flaw was found in some Toyota vehicles, of course, remember this is totally hypothetical and made up, not true, didn't happen, the price for a share of Toyota stock was $127. It steadily declined since. Now in this case, since the stock price is money and you can't divide money up forever and ever, in theory this should be a discrete graph made up of many individual non-connected points. But here's the deal. It would be a little cumbersome to draw so many little points to represent every penny that stock price could have been. So what we kind of do sometimes is we fudge it a little bit. And even though this should be a discrete graph, we often just write it as a continuous graph anyway. And here's a sketch of what that graph might look like. Last example. The United States population was 282 million in the year 2000. It had been growing and has grown ever since. Like the last example, since we're dealing with population, which is a measure of people, it can't be divided up forever and ever. So in theory, a discrete graph would best capture this situation. But there are millions of people in the United States, and of course the population doesn't grow a million at a time. It grows one by one, if you will. And it would be really cumbersome and inconvenient to draw millions and millions of dots to perfectly accurately capture this situation. So while it probably should be a discrete graph, we often graph this as a continuous graph anyway. And here's a sketch of what that graph might look like. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.